Do subscribe to Ekeeda channel and press bell icon to get updates about latest engineering, HSC and IIT-JEE main and advanced videos.
Students, today we'll discuss about another physics paper, JEE Mains Physics 2014. So let us discuss all those questions one by one. Okay. Hello students, let us solve the next question, question number 21. The question is in the circuit zone here. The point C is kept connected to point A. C is kept connected to point A. That means if you close this CA path, this will become a complete circuit. So current will start flowing through this outer boundary till the current flowing to the circuit becomes constant. So current will become saturated, and because this is an inductor, the property of the inductor is that it doesn't want any change in its life. So when current starts flowing through this, it doesn't want the current to flow through this. Initially it offers a very high resistance, and unlike the case of capacitor. So capacitor behaves like a plain wire initially, because it doesn't have potential difference. It behaves like a plain wire. It doesn't oppose. In case of inductor, it is resistance is very high, so it just behaves like like open circuit. So the potential difference is almost equal to this, and as the time passes, the current starts flowing. The rate of it doesn't actually oppose the current to flow; it opposes the rate of change of current to flow. It doesn't want the current to change in its path. So what happens is then? So after a very long time, after t equals infinity, say this current becomes saturated and becomes a plain wire. Then afterwards it doesn't oppose to the becomes steady. So the current becomes steady, becomes constant. Afterward, suddenly the point C is then disconnected from A. C and A was initially connected, now it is disconnected and connected to point B, and here your time starts t equals to 0. Now the battery is disconnected completely. This is the closed circuit having only C and R LR circuit, and time t is equal to 0 starts because already there is current in the circuit because of this. Now it is disconnected. Now this because of that. So what I want to say is that the capacitor and inductor behaves just opposite at the beginning of the circuit and at saturation time. Now the question is that when you connect this, then because the current was earlier flowing in this direction, now by disconnecting, the flow of current will stop. Then it will not stop immediately because it is an inductor. In inductor, it wants the current to flow continue like that. So it will the energy stored in the magnetic field of this inductor will collapse now, start collapsing, and it will try to maintain the flow of current in this direction. So current will flow in this direction. So this will flow in this direction. It will maintain till the magnetic field in the inductor will collapse completely. So current will start flowing in this direction. It will continue in that direction. Now after a very long time or whatever time, the current will stop. Now the ratio, because of the resistance, the current will stop. The heat, that energy will convert into heat. Now you have to find the ratio of the voltage across the resistance. Here, what is the voltage drop, and the inductor. Here you have to find the voltage drop across the resistor, that is VR, and the voltage drop across the inductor, that is VL. You have to find the ratio of these two. At what time? At time t equals to L by R. So basically you have to find VR and VL. It is the now decay of current that will take place in an inductive circuit. and LR circuit. So we have the expression for the decay of current in the circuit is I equals to I naught e raised to minus t by tau. The tau is called the time constant. And that is L by R. So if I substitute that, this becomes I naught e raised to minus t by tau is L by R, so it is R over L. So this is the expression, and this formula expression for current we have to use. And in case of resistance, the potential drop across the resistance VR is the current existing the time into at the time. Which time we're talking about? This time. This t value is this. So this is the general expression for instantaneous current that is present at the circuit. You have to find the inductor at time t equals to this. So at this time, what is the current present? Then I have to put this value of t equals to Ly over here. Then I will get the corresponding current. So this is the current that is flowing through the circuit. So if I know the current that is flowing that time, then I can multiply with this resistance to get the voltage drop. So I will so the resistance is over here and the inductor is here, and this is closed. That point B and C is connected, something like that. Now the current is in this direction, and this is R and this is L, and the current at any time is equal to I naught e raised to minus RT divided L. So putting the value of T equals to L by R given in the question, you will get the current flowing that time. So if I find put that value over there, then I will get I naught e raised to minus R over L into T is L over R. So this will cancel out, and I will get I naught e raised to minus 1. I equals to I naught e raised to minus 1, because this R and this R will cancel, this L and this L will cancel, e raised to minus 1. And if the current is this value, I naught by E, that means it is I naught divided by E. So I naught divided by E is the current that is flowing through this. Okay. Then this is a current that is flowing through this. And if the current flows through that same current will flow through this also. So that current I into R becomes the VR. So voltage across the resistor is I into R. So I multiply R to this value, so it is I naught R e raised to minus 1. This one, I have to multiply only R over here. So this is equation number 1. Now, if I want to know the voltage drop across the inductor, so this is V over L, then it is, I have to use VL. But then in inductor, we know that from Lenz's law that in case of a coil, the EMF induced or the voltage across the inductor equals to minus L di over dt. This is from Lenz's law. So V across L equals to minus L di over dt. So the voltage is determined because of the rate of change of current. This is not because of the current. If current is constant, then this is 0, the voltage drop will be 0. So initially when the circuit was, you can see here, initially it is connected for a long time till the current becomes constant. So when the current becomes constant for a long time, initially when it is kept closed, then when this is constant, then derivative constant is 0, so VL is 0. So after very long time, the potential drop across this will be 0, and and only the total potential drop of the battery, whatever battery is suppose having EMF E, is dropped over here. This doesn't consume any voltage. Now I have this I equation, instantaneous current equation, this value. I have to this one with respect to t. So I have to differentiate this I equation with respect to t. If I differentiate that, I'll get di over dt. If I get di over dt from here, then I'll multiply L or minus L, I'll get VL. So first of all, I have to differentiate this equation with respect to t. So let us do that. So I have I equals to I naught e raised to minus t r over L. I have to differentiate this equation with respect to t. So I will have di over dt, which is derivative of this value, which is I naught is a constant quantity, and derivative of this is e raised to minus t r over L, and derivative of this will be minus r over L, minus r over L. So minus comes out here. So this is like this, and di over dt, I have this expression. So this is minus 1, this is r by L, and this is minus 1. So di by dt is this, and because you know that e raised to minus x, if I differentiate this, then this will become or minus 2x suppose, then it will be e raised to minus 2x into differentiation, this is minus 2. So it is this value, and minus r by L is there, so minus r by L. So the minus okay, I've already given minus, so it is like that. So di by dt is this much. Then E or EMF across the induced across the coil, that is the inductor, or VL, that I say is VL, is minus L di over dt. Now the VR already we have got, and VL we are looking for it, and VL is minus L di over dt is I naught, this value I'll put it here, I naught r by L e raised to minus t r over L. And I must write this as negative because the current is decreasing, so this will become negative, so it will become positive. So here therefore I'll just put it here. So this equals to minus L, and this L will cancel out, and this is I'll write R and I naught e raised to minus t r over L. Again I will put the time equals to L over R given, I put there, then I'll get minus I naught R e raised to minus 1. This is your VL, that is equation number 2. If I use the equation number 1, you can see the equation number 1 is this VR, which is I'll just rewrite this equation over here, R e raised to minus 1. This is equation number 1. If you compare these two equations, then there is only a negative sign, the difference of negative sign. So I will have the ratio of the question is to find the ratio of the VL upon VR or VR upon VL, whichever is the case. The ratio over the voltage drop across the resistor to the voltage drop across the inductor is how much? Then from that equation we have got minus 1. So the option to this question, if I look at the options, then is 1 E upon this minus 1. So minus 1 is the correct answer, because the ratio comes out to be minus 1. Okay, that is the answer to this question. Thank you.